Okay, this is the review video for the material for the final exam that is not in chapters 8 or 9, right? Because the final exam covers mainly chapters 8 and 9, but there are 5 problems from earlier sections. This video addresses those, the things that you need to know from the material earlier in the semester. So first, let's see. Just call this number 1, and the first thing I need you to know is how to solve for the sides of a triangle based off of a given side and a given angle. So this is not laws of cosine and laws of sine stuff. This is more like, well, why don't we need lots of sines and cosines here? Because we're given a right triangle, and we have the nice relationship that if we are given an angle, say a 30-degree angle over here, then since it's a right triangle, I have these nice relationships with the input, this angle being an input, this angle being an input into my trig functions, and each of those trig functions outputting some ratio of the sides. So let me say that this side is y over here, and this side down here is 15, just arbitrarily naming that y just for a variable name. And I said, if I say solve for y, we can go straight to those trig operations that the sine, cosine, and tangent, and the other 3 as well, secant, cosecant, cotangent, though we tend to not use those as much in this kind of problem. I can immediately use the relationship that those trig operations give me, where you input an angle and they output the ratio of 2 sides of the right triangle. I can use those to solve for the missing side. So for instance, I might say cosine of 30 degrees is equal to the adjacent side over the hypotenuse, adjacent to the angle. So this is not useful in this particular example because the adjacent side is this unnamed side over here. Right, so I don't want that. Now I know the hypotenuse is 15, that's the side opposite to the right angle, but I'm trying to solve for y. I need to get that side involved. That side is opposite to the angle given, so that means I want to use the sine function. Sine of 30 degrees is, well, sine of any angle is going to be, in a right triangle, opposite over hypotenuse. That's going to be y over 15. And now at this point, I need to decide what sine of 30 is, right? And I do not use a calculator for this because we can get an exact answer for this, because 30 degrees is one of those nice angles that has a nice relationship. So recall that a 30, 60, 90, if this is 30 degrees here, and this is 90, and then that angle up there being 60, has side lengths, the reference triangle has side lengths 2 for the hypotenuse, 1 for the opposite side, and square root of 3 for the adjacent side. So that means sine of 30 here is equal to 1/2 So y is going to be equal to 15 over 2, just by solving a little bit of algebra, proportions, right? A little bit of algebra here. Y is equal to 15 over 2. Okay, so know how to solve a triangle like this with special angles. A right triangle with special angles, know how to solve for the missing side. By the way, since you will have a unit circle on the exam, do you really need the reference triangle? No, right? Because all you do is you go look at your unit circle That is the ugliest unit circle, but whatever. So I've got the 30-degree angle here. This little coordinate point represents the cosine of that angle. So here's the angle, 30 degrees. The x-coordinate is the cosine of 30 degrees, and the y-coordinate is the sine of 30 degrees. If you remember that, if you know how to use your unit circle and what these coordinate pairs mean, then you're good to go with this problem. You don't need the reference triangle, right? You literally replace sine of 30 degrees with this y value here. There it is, and then you just do the algebra to solve for the missing number. Okay. Okay, let's talk about some inverse trig operations. So say I want you to, well, what would the instructions be? Find the exact value. And I should say here if it's defined, because I could ask something that's not defined. Remember, when we get into the inverse operations, there is a domain issue. If I can ask for something that's not defined, and I'll give an example. Let's do part A. Let's say sine inverse of 3. That's a parentheses there. Let's say part B. Cosine inverse of square root of 2 over 2. Let's also do, let's say, sine inverse of 0. And let's do a tangent inverse of negative square root of 3 over 3. Okay, so what are each of these asking? These are all asking for the angle. The output of each of these should be an angle. So this is asking the question, at what angle does sine output a 3? When you ask what is sine inverse of 3, that's asking the question, at what angle does the sine function output the number 3? Well, this is undefined because you could look at this a couple different ways. First of all, sine only ever outputs between -1 and 1, right? So this is just not possible. Another way, maybe a more direct way of looking at it, is the domain, meaning the allowed input variables for a sine inverse function, is -1 to 1, and thus 3 is outside of that domain, so it's undefined. Okay, so however you like to look at that, either from the sine point of view or the sine inverse point of view, which is more direct. Okay, so you need to know those domains of the inverse functions, the inverse sine, cosine, and tangent functions. Part B, this is a more natural one. At what angle does cosine output square root of 2 over 2? So this is where, again, the unit circle is going to come to your rescue if you don't remember what special angle goes with this particular output. Let's see, I'll draw it down here. You're going to look for an x value on your unit circle. You should look at it and find an x value, because remember, cosine is associated with the x values, right? Just the way the geometry works out. You're looking for values that say square root of 2 over 2. Now you will see that there are 2 of them. There's going to be the pi on 4 angle. Oh, by the way, did I say? Let's do radians. Okay, let's do radians. Okay, so there's an angle pi on 4 that has output square root of 2 over 2, and we don't really care about the y value. It does tend to, or it does happen that it matches. For pi on 4 angles, the outputs of sine and cosine and sine are always matching, though they might be off by a sign, right? But there's another one that yields a positive pi square root of 2 over 2 for that x-coordinate down here, we get square root of 2 over 2, and then for the output of sine, it's negative. And that angle is all the way down here at 7 pi over 4. Okay, so which one do we pick? Which one do we pick? Well, we have to recall that the range of the cosine inverse function ranges from 0 to pi, only the top two quadrants. Because remember, when we talked about these inverse operations, we had to be real careful about, outputting two solutions when appropriate, or only outputting one. In this case, we only want one solution for each of these. So we have to look at the range of the cosine inverse function and say, okay, well, the range of the cosine inverse function only goes from 0 to pi. That's the top two quadrants, and there's only one solution in the top two quadrants, and that's going to be the pi on 4. Okay. What about sine inverse of 0? You could use the unit circle again and go look for y values that are 0. Okay. So you'd see one right here at 1, 0. There's a y value of 0, and you see another one over here at negative 1, 0. By the way, what are the angles that are associated with these two points? This is a 0 degree angle, 0 radians, and then all the way over here is pi radians. Which one is it? So is it 0 or pi? 0 or pi? Well, you have to recall that the range of the sine inverse function is in quadrants not like cosine in 1 and 2, it's in quadrants 1 and 4. So which of the angles, the 0 angle or the pi angle, is in that appropriate range? It's the 0 angle. I'm going to say 0 here. Not 0 degrees. I mean, it doesn't really matter when it's 0, right? 0 degrees, 0 radians means the same thing. But since all these answers I've decided we're doing in radians, so I won't draw a little degree symbol, right? It's just 0. Again, and another way of rephrasing this question is, at what angle does sine output a 0? And you know that at angle 0, sine outputs a 0. Part D is a little bit trickier to do via the unit circle method because tangent does not give you either an x or a y value, right? It gives you a ratio of y over x. So you've got to be, you got to be good with that fraction arithmetic if you want to use the unit circle, because you're thinking about stacking the y over the x value. So what will this one look like? Well, I mean, there are some key things to look for here, like the square root of 3. That square root of 3, that particular number gets involved when you're talking about either a 30 or a 60 degree, like a pi on 6 or a pi on 3, right? So probably thinking about one of those angles. Also, where is tangent going to be negative? Like, let's start narrowing it down. Tangent's going to be negative in the second and fourth quadrant. So you should be looking there. You should be looking there. Oh, and by the way, what is actually really, which one should you be looking for? Well, tangent inverse has the same range output as sine inverse in that it's only going to be first or fourth. So we're looking in the fourth quadrant. And what are those values that happen in the fourth quadrant? Well, we've got this one, right? We got 1, 0. We've got the one down here, which is 0, negative 1, and then we got the one right down the middle, which is square root of 2 over square root of 2, negative square root of 2 over square root of 2. So that none of these are right, because y over x here, that's 0 over 1, that would be 0. It's not what I'm looking for. This would be undefined, right? Negative 1 over 0. This would be this thing over this thing, which would just end up being negative 1, because they exactly match, except one's negative. So none of these so far. So let me look at, what about this angle here? That, and then this one here as well. And what are those? Let's see, I don't have my unit circle in front of me, but let me just say this 30 degrees, so that's the adjacent side is square root of 3 over 2. Hang on, am I messing this up? No, that's right. Square root of 3 over 2 comma negative 1/2. That's this one. And then this one, which I'm almost out of room, is going to be the opposite, 1/2 comma negative square root of 3 over 2. Okay, so what do we do now? Well, what I would do is I would go stack these. You know, if I really wanted to be absolutely sure which one I'm supposed to use, I mean, I know it's got to be one of these two, right? It's either this this angle here or this one here. So let me just stack those. Let me take this coordinate point, square root of 3 over 2. So this is what I would call like the unit circle method, which why not do it this way, right? Because if you've got a unit circle. So now, and I'm keeping in mind that tangent of theta is equal to y over x. So let me go ahead and stack these, y over x. Negative 1/2 over square root of 3 over 2 is the same as negative 1, so I'm doing this one first. Negative 1/2 times 2 over square root of 3. So hopefully you see what happens. So, you know, just changing this division symbol to a multiplication and taking the reciprocal of that bottom fraction. So I'm getting negative 1 over square root of 3. So maybe you stop at this point and you say, maybe you know I shouldn't stop, but let's say you do stop and you say, okay, let me check the other one then. So stack negative square root of 3 over 2 over 1 over 2. That's going to be, hold the first, change the operation to multiplication, and flip that bottom. Okay, so neither of them are looking like what I want. Negative square root of 3 over 3. So what happened? Did I pick the wrong angle? No, it's just a little bit more algebra, right? Rationalize the denominator, and you get negative square root of 3 over 3. How do you rationalize the denominator? Remember, that means you get that radical out of the bottom by multiplying by 1 in the form of that square root in the top and bottom. Square root of 3 times square root of 3 is square root of 9, which just outputs a 3. In other words, the radical just pops off. And then in the top, that's what you get. So you have to be careful here. You have to be careful about with tangent, in particular with tangent, because of the way it stacks these. If you're doing it via looking at the unit circle, the way it stacks these coordinate points, the y over x, you got to be real careful. So which one was it? It was this one. Which back here, so I'm going to scoot this. That was this one. Now, what do I call this angle? There's so much going on here, right? What do I call this angle? Well, recall that the range of the tangent inverse function goes from negative pi on 2 to pi on 2. So I do not extend outside of that range and come all the way around and call this 11 pi over 6, right? I do not go all the way around and call it 11 pi over 6, even though that's what you might see it as in the unit circle. Actually, by the way, the unit circle I'm giving you on the exam is in degrees, so you will have to you will have to make sure that you know the unit circle in radians too. You can just convert them, right, if you need to. Okay, so I don't want to call it a 11 pi over 6 angle, because that goes outside of my range. So what I do is I go from here to name the angle, to stay within that negative pi on 2 to pi on 2 range. So that means I'm going to call this a negative pi on 6. There's a lot of subtleties going on, especially with the tangent function and the sine inverse function. You would have to do this as well, though I gave a nice easy one here for sine inverse that was right down the middle. But if you ended up with an output for a sine inverse down here somewhere, you would want to give the negative angle, because again, you don't want to go outside of the range of the inverse function and wrap all the way around to hit an angle in the fourth quadrant. You want to come backwards from the x-axis down Now again, we did not see that in part C here because this is a special case right at 0, right? So we'll just keep that in mind. Okay, what's next? Also make sure that you know the law of sines and law of cosines. I'm not gonna add that in here because there's like separate videos that are nice and fresh up in in the modules page. So what is the next thing? Graphing is the next thing if I'm going in order, but I'd like to go to a solving equation problem first because it involves inverse trig stuff. So it's going to flow more naturally from that last problem here. Let's say we have cosine of theta is equal to 1/2. Solve the equation. And enter answers, or write answers. This is how you would see it in the homework or in the exam as a comma separated list. Let k be any integer. So, okay, what is all this about? Well, remember when we talk about solving equations, now we are going to abandon this notion about the range of inverse functions, and we're instead thinking about them as operations. So what does that mean? That means that we're going to accept any solution from any quadrant that is appropriate. Well, only 2 quadrants, well, ever at most 2. Not only that, so not only will we have 2 solutions to this equation, but we also want to be able to mention or take any rotation of each of those 2. So if I have some solution up in some quadrant 1 of my unit circle, I'm also going to have another solution somewhere else in some other quadrant, and then also I want to mark or note the infinitely many solutions that can come from extra rotations that always land at that angle. Okay, so let's get started with this one. Okay, what do we do to solve for theta? Do you divide by cosine? No, cosine's not a number, it's an operation, right? You have to take the inverse on both sides. What does that look like? Take the inverse on both sides. Cosine inverse and cosine cancel each other out, and I'm just left with cosine inverse of 1/2. Okay. And now I'm thinking about this as an operation, not a function, so I want both solutions to this. How do I find those solutions? I go look for those angles. I'm going to write them in radians. That give me on my unit circle that have an x-coordinate of 1/2. So that would be the the pi on 3 up here. This would be a pi on 3. It would have 1/2 comma square root of 3 over 2. That's the pi on 3. And the other one would have to be down here. 4 pi on 3. Whoops. Okay. And again, I'm not worried about going outside the range of this cosine inverse thing anymore because, hang on, let me write this down. Because I'm thinking about it as an operation and not a function right now. Okay, so my 2 base angle solutions are going to be pi on 3 and 4 pi on 3. Okay. So theta is going to be equal to, now watch how I write this. I'm going to say pi on 3, and then I'm going to leave some space, and then comma, so leave some space, and then 4 pi on 3, and then some space here. And remember, though, that I don't just want the base angle of each one. I want every rotation. So what does each rotation look like? Well, it's a whole 2 pi, so I'm going to add a whole 2 pi. But for any kind of rotation, any number of rotations, backwards, forward, counterclockwise, clockwise, so that can be represented by that k, that they say let k be any integer. That k is going to represent any number of full rotations, either clockwise or counterclockwise. And I add that to both of my base cases here. So will these things always have two solutions? Well, it depends. It depends on the operation, whether it's sine, cosine, or tangent. It depends on where it's landing, like if it's landing on an axis or something. Just the safest way is to solve it like this. Go find the angles that satisfy this via the unit circle, and then take those as your base angles, and then add 2 pi k to both of them. Oh, but it's not 2 pi k for tangent. Keep that in mind, right? Because the period of sine and cosine is 2 pi. A full rotation is 2 pi, but for tangent, it's different. Keep that in mind. For tangent, it's pi, right? A full rotation, well, I should say its period is pi. So it only takes tangent 1 pi to get all the way back around to where it started. So you would add pi k, not 2 pi k, to the solutions if it was a tangent function. Okay. Finally, let's talk about graphs. Just want you to know some basic stuff about graphs. In fact, I might even just say, I won't even work a lot of problems. I'll just kind of punt this to you as the student. Know the basic trig function graphs. So that means the three main trig functions, the sine, cosine, and tangent. So sine and cosine are very similar to one another. In fact, they are the same graph, just phase shifted a little bit. Tangent's wild, right? It's completely different. It has those repeated vertical asymptotes, so make sure you know that. Don't worry about secant, cosecant, or cotangent. So know the, here, I'll very quickly draw, let's see, cosine. Oof, that's rough. There's a basic cosine graph. So it's period from 0 to 2 pi. This would be 2 pi here. There's a full rotation. Here's pi happening in the middle. And then these values of pi on 2 and 3 pi on 2. This is a full period of the cosine function. There, that's a period of it, and then there's more. This is cosine. I hope I said that right. Yeah, this is cosine. And then sine, looking very similar, except starting at 0. And so starting at 0, and then maxing out at pi over 2, and then hitting 0 again at pi, and then maxing out again at 3 pi on 2, though in the negative direction, and then hitting 0 again at 2 pi. And by the way, what are these max values? They're 1 and -1, right? So this is 1 here, and this would be -1 down here. Unless it has been expanded, if its amplitude is bigger than 1, when a number is multiplied up front. So know that too. So I'm going to leave some room for the tangent function that I'm going to say also. Know how changing amplitudes change the picture. In other words, if you were given a function like f of x equals 3 sine x, what does that do to the graph? Okay, so know that. So I'm not done writing the basic trig functions here, though. The basic trig function, the last one being tangent. So to draw this, let me put pi on 2 here and a 3 pi on 2 out here. So, oh goodness, have I messed this up? Negative pi on 2. So it's got vertical asymptotes at each of these pi on 2's. Wait a second. Yeah, okay. And it's going to come up like this and approach that asymptotically, and then it's just going to keep doing that with a period of pi. So at every pi on 2, it's going to have a vertical asymptote. And by the way, does the changing the amplitude of the tangent function, does that really do much? Well, not really, because what does it do when you change the amplitude? It stretches the function up and down, right? It increases the size of these waves and troughs. And on a tangent function, I mean, all you're making it do is go to infinity slightly faster, right? So, but let me write this down, tangent. Okay, so that's pretty much all I want you to know for the graphs. There's a whole lot more to know, though, right? About phase shifting, like moving it up, moving it left to right by adding and subtracting stuff inside of the input of the function, or moving it up and down by adding or subtracting stuff outside of the function. You can negate the outside of the function to flip them upside down over the x-axis. Lots of different transformations of graphs, but the main thing I want you to know is the basic shapes, and then know how changing the amplitude on the sine and cosine in particular, how that would change the picture, and what the highest and lowest values would be. Okay, that is it. You are going to have a formula sheet. I think I've already said that a few times, but it is, just to remind you, it's in Canvas under modules. It says formula sheet for final exam. It's right underneath where the syllabus is in Canvas. So you will have that on the final exam. That's going to be a big old formula sheet with a whole lot of stuff on there. Not all of it is relevant for us. We didn't cover all of this stuff. And then a nice unit circle that is in degrees. So you need to make sure you are comfortable knowing what these degrees are as radians, because some of the exam obviously is going to be in radians. Or either asking for the answer in radians or the problem will be in radians. So make sure you're good with going back and forth between degrees and radians. Okay, that is it.